We live at the bottom of a well we cannot see. Every breath, every step, every rising tide is shaped by something that does not shine, does not roar, and cannot be held. And yet without it, nothing would stay. Not stars, not moons, not us. Gravity. To most of us, it feels like a pull. A force tugging us down. Apple to earth. Human to ground. Planet to sun. It's familiar. Unquestioned. Almost comforting. But gravity is not what it seems. Long ago, we thought the earth sat still while the heavens spun around it. Then we learned the earth was moving, then that it was falling, forever falling around the sun. But even then, we imagined a cosmic hand reaching across the void to pull one body toward another. And for centuries it worked. Newton's equations could launch rockets, guide moons, and land humans on other worlds. But they never explained why. Why should anything reach across empty space to tug on something else? What was this force, invisible and instantaneous? Then, in the early 20th century, a man looked deeper. He didn't see a force, he saw a shape. Albert Einstein imagined space not as a stage, but as a player, fabric, a geometry that bends and warps under the weight of matter. And he realized that what we call gravity is the path things take through this curved fabric. The Earth doesn't pull the moon. The moon rolls through a valley in space-time dug by Earth's mass. You don't fall to the ground because something grabs you. You follow the straightest possible line through a universe that isn't flat. This episode is a journey into that quiet curve. We'll explore how Newton's truth gave way to Einstein's revolution, how gravity isn't a force, but the shape of reality itself, and how, by understanding this shape, you begin to understand everything. The rise of mountains, the flow of time, the birth of stars, the end of the universe. All drawn by gravity's invisible hand. Not a force, a form, an architecture written into the structure of space-time. The universe doesn't pull you down. It guides you along the curves it has drawn, and those curves are everything. In the 17th century, the universe was still divided. The heavens were one thing, distant, eternal, unknowable. The earth was something else, chaotic, heavy, mortal. Stars moved with divine elegance. Stones fell with earthly certainty. But no one believed the same rulebook could apply to both. And then came Isaac Newton, a man who lived through plague, through silence, through solitude. And in that solitude, he glimpsed something extraordinary. He saw unity. They say it began with an apple, but the truth is far more profound. Newton asked a question that split history in two. What if the force that pulls the apple down is the same that holds the moon in orbit? This was not just science, it was alchemy. It took the chaos of motion and turned it into a single, universal law. With one equation, he connected sky and soil. F equals g, r squared force equals the product of two masses. Divided by the square of the distance between them, it's multiplied by a constant. This was gravity not as divine will, but as math, and suddenly everything moved with purpose. Planets became predictable. Moons became mechanical. Even the tides were no longer mystical, they were measurable. This was the dawn of the clockwork universe. But something haunted Newton's visions, something he never solved. His law described gravity perfectly, yet it gave no clue how it worked. The force seemed to act instantly across empty space. No ropes, no air, no touch. The sun, 150 million kilometers away, tugged on the Earth as if it were right beside it. How Newton himself was uneasy. He called it action at a distance, and admitted he had no idea how mass could influence mass across a void. I frame no hypotheses, he wrote. Hypotheses non fingo. In those 3 words, Newton did something rare. He confessed ignorance, without denying truth, and still, his equations worked. They launched cannonballs and calculated eclipses. They could predict when Halley's Comet would return, centuries in advance. They explained the fall of an apple and the fury of a hurricane. The Enlightenment world embraced Newton's vision like gospel. To many, he wasn't just a scientist, he was the final word. But science doesn't rest forever. And as the centuries rolled on, the cracks began to show. Take Mercury, the innermost planet in the solar system. Fast, hot, elusive. Its orbit didn't behave quite as Newton predicted. Tiny discrepancy. A wobble at first dismissed as error, then investigated, then persistent. Some blamed another unseen planet Vulcan, but it wasn't Vulcan. It wasn't error. It was a signal. The old model, elegant as it was, had limits. And then there was the speed of light, finite, measurable. If gravity was truly instant, how could that be? How could one part of the universe know what another was doing, faster than information itself could travel? Newton's spell was holding. But it was no longer enough. His equations described a universe that was stable, mechanical, absolute. But the real universe wasn't. It pulsed, it curved, it evolved. It needed a new idea, one that went beyond the force of gravity and reached into the shape of the world itself. And so, after nearly 250 years, it happened. A young patent clerk in Switzerland, armed with thought experiments and a mind like no other, reimagined everything, not by erasing Newton, but by completing him. At the dawn of the 20th century, the universe still ran like a clock. Newton's equations had survived for more than 200 years, tested, trusted, and triumphant. Engineers used them to build bridges, astronomers used them to map the heavens, and yet, beneath their elegance, a quiet question persisted. Something didn't fit. Mercury's orbit was misbehaving. The speed of light measured in laboratory after laboratory refused to bend to Newton's laws. And no one could explain why gravity seemed to act instantaneously, as if distance didn't matter. In the town of Bern, Switzerland, a young patent clerk sat at his desk, reviewing other people's inventions. But his mind wandered far beyond the margins. His name was Albert Einstein, and he wasn't just thinking about machines. He was thinking about light. Einstein's first great insight, special relativity, was published in 1905. In it, he shattered to deeply held beliefs that time is absolute and that space is the same for everyone. Instead, he proposed that time slows down when you move faster, that lengths contract, that simultaneity, what we think of as now, is relative. Space and time, he realized, weren't separate things. They were woven together. One fabric, four-dimensional, dynamic. He called it spacetime. But there was a problem. Special relativity worked beautifully for objects moving at constant speeds. But it couldn't explain gravity, couldn't explain falling. So Einstein kept thinking, and one day he imagined something simple, something profound. He imagined falling in an elevator. In that moment, Einstein asked, "What would I feel if the cable snapped?" The answer surprised him. Nothing. He'd float, as if gravity had vanished. The walls would drift beside him. His feet would no longer touch the floor. He'd be weightless, and yet he hadn't left the Earth. This became the foundation of his next great theory, the equivalence principle, the idea that gravity and acceleration are locally indistinguishable. If you're in a windowless room, you cannot tell if you're in deep space accelerating or standing still on a planet. To Einstein, this wasn't a coincidence. It was a clue. Gravity wasn't pulling. Something else was happening. And so Einstein began to imagine space and time not as a backdrop, but as an actor in the play. He saw that mass and energy deform space-time. They cause it to curve, to flex. And objects, planets, light, even you follow the curves. Not because something is pulling them, but because space-time itself is shaped in a way that makes falling the straightest path in physics. These paths are called geodesics, the closest thing to a straight line in a curved world. The Earth doesn't orbit the sun because of a force. It rolls through the sun's curved space-time. Like a marble spinning in a bowl, the apple doesn't fall because the Earth pulls it. It follows its geodesic downward because Earth has bent the world around it. Einstein's insight was radical, and yet it made sense of everything Newton couldn't explain. Gravity, he realized, is not a force. It is geometry. In 1915, he wrote it down. A set of 10 interlocking equations, fierce, beautiful, and profoundly compact. They're known today as Einstein's field equations. They describe how matter and energy shape the curvature of space-time, and how that curvature, in turn, guides the motion of matter. As physicist John Wheeler would later summarize, space-time tells matter how to move. Matter tells space-time how to curve. In those words is the essence of general relativity. It was a new way of seeing the universe, no longer a machine, Now, a sculpture. A living, breathing structure of curves and contours shaped by the presence of stars, black holes, even light itself. Space and time were not static. They could ripple, bend, stretch, collapse, and though Einstein didn't yet know it, his theory would predict the unimaginable: wormholes, black holes, gravitational waves, the shape of the cosmos itself. It would be decades before many of these ideas could be tested. But already, general relativity offered something more than science. It offered poetry. The universe, it seemed, had rules. Those rules were not chains, they were curves. And in every fall, every orbit, every echo of cosmic motion, we are tracing the shape of reality itself. You are falling right now, not metaphorically, not emotionally, physically, constantly. Your body is tracing a path through the curved fabric of spacetime, drawn not by force, but by form. But there's a catch. You don't feel like you're falling. You feel solid, supported, anchored. Because the floor beneath you is stopping you from following your natural path. It's pushing up ever so slightly, counteracting the curve you were born to follow. This is gravity. It's not a force that pulls you down, but a shape that you are forever trying to fall through until something resists. Imagine being inside an elevator, one that suddenly breaks loose and falls freely. In that moment, you feel weightless. Your stomach lifts. You begin to float. That's not science fiction, it's physics. You're not being pulled down. You're simply being allowed to move, naturally, unimpeded by the floor, by walls, by friction. Now imagine that same elevator, but this time in deep space. Engines fire beneath it, accelerating upward. Inside, you'd feel gravity again. Pressed to the floor, convinced of a downward pull. But it's not pull, it's the floor accelerating into you. This is the genius of Einstein's insight. Gravity and acceleration are the same. The reason you feel your weight isn't because the earth is pulling you down. It's because the ground is pushing you up. It's preventing your fall. You are trying to follow the straightest path through curved spacetime. And everything you call gravity is resistance to that. Now look up. Look at the moon. It's falling too constantly, but it never hits the earth because it's falling sideways. Fast enough that every step it takes, the earth curves away beneath it. That's what an orbit is. A controlled fall. A dance between motion and curve. No tethers, no pulls. It's just momentum and the shape of the stage beneath. Planets orbit stars. Moons orbit planets. Satellites orbit Earth. They are not suspended. They are not held. They are moving freely, riding the contours of curved spacetime. Even time itself is caught in the curve. Einstein's theory predicted something extraordinary. Gravity slows time. Wherever spacetime is curved more steeply, like near massive planets or black holes, time itself flows more slowly. This isn't speculation. It's measurable, testable, and essential to daily life. The GPS in your phone depends on satellites above Earth, where gravity is weaker and time flows just a little faster. If we didn't correct for that difference, your location would be off by kilometers and minutes, so every time you check directions, you're trusting general relativity. This is the quiet revelation of Einstein's universe. We are not being pulled. We are being redirected. Our lives unfold along curves we cannot see but constantly feel. You stand still on Earth, but you're not at rest. You're being held in place, deviating from your natural motion. That pressure beneath your feet, that's not gravity. It's resistance to gravity. Resistance to the path your body is trying to take. And when that resistance vanishes, you float. Astronauts in orbit aren't weightless because gravity is gone. They're weightless because they're falling forever, and nothing is in their way. We live inside this geometry. It shapes the path of rivers, the birth of stars, the flow of time itself. It sculpts galaxies, bends light, and breathes motion into the cosmos. We are creatures of this curve. Each step, each breath, each heartbeat is drawn along invisible lines. Einstein gave us more than equations. He gave us a new way of seeing, not a universe of forces, but of forms. Not a pull, but a path. Not weight, but a curve beneath our feet. The next time you fall, remember, you are not being pulled down. You're being guided, gently, precisely by the shape of the world itself. Great ideas must do more than dazzle the mind. They must face the universe, survive. Einstein's vision of gravity as geometry, not force, was beautiful. But was it true? Didn't take long to find out. And the first proof was waiting close to home in a tiny, fast-moving world scorched by the sun. Mercury. For centuries, astronomers had tracked Mercury's orbit with increasing precision. They noticed something strange. Each time the planet swung around the sun, its closest approach shifted slightly, like a slow, elegant spiral. Newton's equations could explain most of it, almost all, but not all. There was a sliver left unexplained, a mystery. Einstein ran the numbers using his new equations, and what Newton couldn't explain, general relativity nailed perfectly. The curvature of spacetime near the sun, especially for a planet so close, was just enough to twist Mercury's path. Not wildly, just enough. The mystery had lasted for centuries, and it dissolved in a single equation. Still, the world wasn't ready to believe. Einstein needed a second test, and it came ironically from something he couldn't see. Light, according to Newton. Gravity shouldn't affect light at all. Light has no mass, nothing to pull. But in Einstein's universe, mass bends spacetime, and light, like everything else, follows that curve. So light passing near a massive object should bend, not because it's pulled, but because the path itself is warped. And the perfect test? A total solar eclipse. In 1919, astronomer Arthur Eddington led expeditions to Brazil and West Africa to observe stars near the eclipsed sun. For a few precious minutes, the sun's brightness would be blocked, revealing background stars. If Einstein was right, their positions would appear slightly shifted, distorted by the sun's warped spacetime. And when the data came back, they were. The stars had moved. The invisible had cast a shadow. Einstein's theory wasn't just correct. It was verified. The headline in the Times read, "Revolution in Science. New Theory of the Universe." Einstein went to sleep a quiet physicist. He woke up a legend. But this was just the beginning. Over time, scientists realized that this warping of light wasn't rare. It happened all over the universe. Massive galaxies, and even whole clusters bin light from galaxies behind them. The effect is called gravitational lensing. It lets us see things otherwise hidden, distant galaxies, invisible matter, even the cosmic web itself. Today, telescopes across the world, and it orbits use these natural lenses to peer deeper into space than ever before. All because Einstein dared to say, light follows the curve. But the most radical prediction of Einstein's theory wasn't bending. It was collapse. His equations allowed for a terrifying possibility. What if mass curves space-time so severely that it creates a hole, a place where gravity becomes infinite, where time stops, where not even light can escape? A black hole. At first, Einstein himself doubted they were real. So did most scientists. It was too strange, too absolute. But as decades passed, evidence piled up. Stars orbited invisible objects at blistering speeds. X-rays screamed from places where no star could be seen. And in 2019, humanity captured the unthinkable. An image of the shadow of a black hole, its event horizon glowing against a field of fire. Einstein never lived to see it, but his equations predicted it all. Still, there was one more test. It's the boldest of them all. Einstein's math didn't just allow for curved space. It allowed for ripples, waves in spacetime itself, just as a pebble sends circles across water. Massive events like merging black holes could send tremors through the very fabric of reality. For 100 years, this remained theory. Until September 14, 2015. That's when an observatory in the United States, Liggett, detected something extraordinary. A tiny stretch, a fleeting compression. The unmistakable signature of two black holes colliding a billion light-years away. Space-time had rung. And we heard it. For the first time in history, humanity had sensed not just the contents of the cosmos, but the shape of the void itself. Einstein's equations were no longer just ideas. They were instruments. They explained Mercury. They bent starlight. They predicted black holes. They rippled across the universe and arrived on Earth. All of it traced back to a man who imagined falling in an elevator. A man who believed the universe wasn't driven by forces, shaped by form. And the universe answered yes. We all grow up believing the same thing. That gravity is a force pulling us downward. That the earth is tugging at us. That something invisible grabs us and holds us close. We feel it when we lift a suitcase, when we fall from a tree, when we stumble and hit the ground. It feels real, obvious, intuitive. But what if it's all an illusion? What if what you call gravity isn't gravity at all? Let's go back to basics. You're standing still, feet flat, spine straight. You feel your weight pressing down through your shoes. That sensation, that downward push you call gravity. But it's not gravity, it's the floor. The earth is pushing you upward, ever so slightly, constantly, keeping you from moving along your natural path through curved spacetime. That pressure on your feet, that's not pull, it's resistance. Gravity, as Einstein showed, isn't a force pulling you down. It's the shape of space telling you to move in a certain way. And when something stops you from moving that way, like the ground, that resistance is what you feel. Now imagine falling off a chair. In that brief, suspended moment before you hit the ground, you feel something strange. You feel nothing, no weight, no pressure, no resistance. You are in free fall. And in that moment, you are finally obeying the curve. You are not being pulled. You are being allowed to move as space-time tells you. This is why astronauts appear weightless in orbit. They are not beyond gravity. They're still well within Earth's influence. They are falling constantly around the planet. Nothing resists their motion. Nothing pushes back. And so they float, not because gravity is gone, but because nothing is stopping it. This is one of the most counterintuitive ideas in all of physics. The very sensation we associate with gravity, weight, heaviness, pressure, is not a sign of gravity acting. It's a sign of gravity being interrupted. When you stand still, you are not at rest. You are being accelerated upward by the ground beneath you, nudging you off your geodesic, the path you would naturally follow through space-time. When you jump, for a split second, you return to the curve. You follow the shape, and you feel free. This is why astronauts train in free-fall flights. Why black holes feel so strange to describe. It's not because there's more gravity there, it's because the illusion of force has vanished. In physics, we have a name for this kind of deception: fictitious forces. When you take a sharp turn in a car and feel pulled to the side, you aren't really being pulled. You're trying to continue in a straight line, but the city is pushing you away from that path. The so-called force is an artifact. An illusion born from resistance to natural motion. Gravity works the same way. We call it a force because that's what it feels like. But in Einstein's world, force doesn't make things fall, shape does. And when we allow ourselves to follow that shape, when we're in free fall, we feel nothing. So what is weight? It's not a property of your body. It's not something you carry like a backpack. It's a relationship between you and the surface, preventing you from obeying gravity. A truck on a mountain has weight because the ground resists its descent. A feather drifting in air has less because resistance is small. An astronaut in orbit has none because there's no resistance at all. Your weight is simply the force required to keep you from falling. And if you stop resisting, you're gone. You move, you fall, you return to the curve. This is why general relativity isn't just a new equation, it's a new way of seeing. It tells us that gravity isn't acting on you, you're acting against it. Your weight is your own defiance. When you stand, you fight the curve. When you fall, you surrender to it. We are so used to associating gravity with force that we miss the deeper truth. Gravity at its heart is not an agent. It is a guide. A silent architect shaping how things move, not because it pushes or pulls, but because space itself is curved by the presence of mass and energy. In Newton's world, a cannonball falls because the Earth pulls it. In Einstein's world, it falls because Earth has bent the path beneath it. The ground interrupts that motion, and the cannonball slams into resistance. The Earth never reached out, sky never pulled down. The illusion of force was ours. When we reframe gravity this way, everything begins to change. We see the Earth not as a puller, but as a bender of paths. We see falling not as failure, but as alignment. We see weight not as a burden, but as a signal, a quiet reminder that we are being held against our natural motion. And somewhere in that realization, the world becomes more than physical. It becomes poetic. We are born in motion, guided by curves, shaped not by forces, but by the space we occupy and the paths we're allowed or denied to follow. No map is perfect. Even the best ones, beautiful, elegant, astonishingly accurate, eventually run into places they cannot describe. And Einstein's theory of gravity, for all its brilliance, is no exception. For over a century, general relativity has guided spacecraft, predicted cosmic phenomena, and reshaped our view of the universe itself. But at its edges, it begins to whisper nonsense. To truly understand the shape of gravity, we must visit the places where that shape collapses, where spacetime folds too tightly, or unravels altogether. We must travel to the edges of the curve. First, the black hole. Einstein's equations predicted them reluctantly. Even he was unsure they were real. But now we know they're everywhere, lurking at the hearts of galaxies, spinning in binary pairs, swallowing stars whole. A black hole is what happens when gravity wins. When mass bends spacetime so deeply that escape becomes impossible. Not even light can flee. But go deeper still past the event horizon, into the core, and Einstein's map tears apart. Here lies the singularity, a point of infinite density, infinite curvature. It's not a place, but the breakdown of place. It's not a thing, but the collapse of all things. Our equations scream. They yield infinities. They lose meaning. And general relativity, for all its strength, admits its limits. It happens again. At the beginning. 13.8 billion years ago, the universe was born, not in space, but with space. Time didn't tick forward from nothing. Time itself ignited. The Big Bang wasn't an explosion in space. It was the expansion of space itself, from something infinitely hot, infinitely dense. Once again, the equations spiral into singularity. Space-time begins at a point, but what lies beneath that point? No one knows. Einstein's theory cannot tell us. It was never meant to. At both the beginning of time and at the centers of black holes, the curve becomes too steep, and our understanding falls off the edge. And then there's something stranger still. We once believed the universe's expansion would slow, perhaps halt, maybe even reverse. Gravity, after all, pulls everything inward. But in 1998, two independent teams observed something shocking. The expansion wasn't slowing, it was speeding up. Galaxies weren't just drifting apart, they were being driven apart. As if space itself had grown restless. Call it dark energy. An unknown force or field that opposes gravity, accelerates expansion, and dominates the cosmos. It's not in Einstein's equations, at least not directly. We've tried adding it as a cosmological constant, but it feels like patchwork. The truth, don't know what it is. We don't know why it's there. We only know this. Gravity on the largest scales is losing. And on the smallest scales, gravity disappears. In the realm of the very tiny, the subatomic, the quantum, another theory reigns. Quantum mechanics. Here, particles aren't particles at all, but waves of possibility. Cause and effect blur. Time becomes uncertain. Reality seems stitched from probabilities. Quantum theory is wildly successful. It explains the structure of atoms, the behavior of light, the chemistry of life, but it has no room for gravity. When we try to insert general relativity into quantum mechanics, or vice versa, the math implodes, equations become meaningless, predictions break. There are two masterworks, written in incompatible languages. One bends the fabric of the cosmos. The other quantizes energy in discrete chunks. So far, no one has found the bridge between them. Physicists call this the problem of quantum gravity. We've tried answers. String theory, which replaces particles with vibrating strings in 10 or 11 dimensions. Loop quantum gravity, which tries to quantize spacetime itself. Emergent gravity, where gravity isn't fundamental, but rises from something deeper, like temperature emerges from molecular motion. Each is bold, each has potential. None are proven. And so we stand at a precipice, looking at a map that works astonishingly well, but only on half the terrain. Einstein gave us the shape. But beyond that shape, the extreme, the infinite, the atomic, a deeper truth waits. Perhaps the next Einstein is already among us. Perhaps they are sketching equations on a chalkboard, or staring at simulations, or simply thinking about falling, like Einstein once did. Whoever they are, they will do what Einstein did to Newton, not erase the map, but complete it. Extend the curve, smooth the edges, unite what has never been united. Gravity and the quantum, the curve and the quanta, geometry and uncertainty. And when they do, our understanding of gravity may change again just as profoundly. What we now call curvature may be something else entirely. The stage may become a dancer. The dancer may become a song. But for now, we remain here between certainties. We know gravity curves space. You know that curve guides planets, light, and time itself. You know it breaks its singularities and weakens against dark energy. We know it vanishes in the quantum world. No, it is not a force. But we also know it is not the end of the story. Gravity was once a mystery. Then it became a force. And we know it was never either. It is a shape. It's not something that pulls, but something that guides. A silent curve beneath all things. A hidden architecture that doesn't push or tug, only bends, invites, redirects. From the fall of an apple to the orbit of galaxies, it is the same rule. Not enforced by pressure, but followed by motion. We do not fall because something grabs us. We fall because the universe is shaped that way. Einstein's gift was not to add new forces to nature, but to subtract illusion. To peel away centuries of habit and reveal something simpler, stranger, and more elegant. Space is not a container. Time is not a clock. Together they are a stage, malleable, active, alive. Mass tells spacetime how to curve. Curved spacetime tells matter how to move. This was not a new law, but it was a new language. And once we learned to speak it, the universe spoke back. It spoke in the orbit of Mercury, in the warping of starlight, in the silence of black holes, and the trembling of gravitational waves. It spoke in equations that bent across a century and still hold, in images of cosmic lensing, in clocks that tick slower on mountains than at sea, and it speaks, still in every step you take. In the pressure beneath your feet, in the feeling you call weight, in the fall you call motion, you're always obeying the shape, even when you resist it, especially then. And yet, this shape is not the end. At the center of black holes, and at the beginning of time, the curve becomes chaos. Their gravity breaks, and something deeper waits. We do not know what it is. Only that the laws we hold now, for all their beauty, are not the last. Somewhere, the next truth is forming. Another shape, perhaps, or no shape at all. But for now, we stand in a universe carved by curvature. And to live within it is to participate in its motion. To fall is to follow. Gravity is not what holds you down. It is what guides you forward. Not a force, but a form. Not a command, but a path. To understand it is to understand the world, not as a machine, but as a motion, not as pulled, but as shaped. This is the laws behind everything. And this was gravity.